So we have new APIs and new features. At the same time, the web is evolving. So you have new standards, which would be supporting HTTP 1 to HTTP 2 to Quick, HTTP 3, and browsers need to have support for all of these existing protocols. At the same time, you have websites that are growing bigger and turning into progressive web apps. And when you need browsers to support them, they need to add new mechanisms, new features through things like service workers. Over a year and a half or 2 years ago, Google also had proposed and it's continuing to propose a bunch of new mechanisms through the Privacy Sandbox project, where they're trying to phase out third-party cookies, but they're replacing them with a bunch of new mechanisms, which would be like trust tokens, the Fledge API, the Topics API, all of it. Another part is that tracking users across the web is ubiquitous. It is crucial. It is an integrated part of things like analytics to understand which parts of your websites are performing well, which parts are not. Say a user's logged in, how do you personalize things that they see and their experiences? They assist in two-factor authentication. But they're also known for some privacy invasive use cases, which is third-party advertising. The way they re-identify users, so you visit the same website, you visit a website across sessions. The most popular way that we know is through cookies, first and third party. But when browsers added support for new types of storages like local storage, IndexedDB, or the HTTP disk cache, all of that has been growing in its use for tracking, re-identifying users. There's another aspect to this, which is for over 2 decades, we've known of this larger umbrella of mechanisms that we call ever cookies or super cookies. So when browsers used to support Flash plugins, it used to be Flash cookies. But even more recently, we've seen how things like the HSTS preload list can be abused. Or even a couple years ago in this conference, you had the favicon cache that was shown as a benign mechanism that could still be used to store arbitrary data and track users across the web. When browsers continue adding these complex mechanisms and APIs, these mechanisms need evaluation. So we don't end up in positions where you just find out about known tracking vectors being applied to new mechanisms as well. When they add support for new features as they're introduced, these may cover client-side storage, data, access control, things like that. But when they are adding these things, they're not testing them completely. And understandably so, because testing is tricky. These browsers are massive code bases. They're handled by different teams that are responsible for different platforms, different aspects of the product. It's understandably hard to get a comprehensive testing suite or a testing framework that covers all contexts in which these mechanisms can be accessed. But over the last few years, and this has been a good thing, where security is increasingly becoming an integral part of testing, and it's not an afterthought after the product's out there. But privacy is not in the same place. It's not introduced. It's not thought of as something that needs to be comprehensively evaluated in a systematic fashion. So we had this one simple observation based on which we developed this paper, which is that any mechanism that affects any client-side data or affects the state of any policy implemented on the client side, on the browser, can be at least considered to be a potential tracking vector. So with our framework, which we're calling CanITrack, we do exactly this. We develop a streamlined approach that comprehensively tests the accesses that can be made to any mechanism across sessions, across a bunch of contexts. So that would be first-party accesses, third-party accesses, thinking of getting this same state read in private mode. Does it persist despite the user having cleared their browser data? And all of it, to be able to support this wide range of requirements that different mechanisms have, we introduced the framework such that it relies on interacting with any new mechanism just based on a read method and a write method, which is called on the client side, and any additional implementation for the mechanism is not interacted with. I'll make that a little more clear in the next few slides. Here's an overview of the framework. well, take you through it, but largely it starts from the left side, where the user provides information about what mechanism they were trying to test and how it needs to be accessed. The larger box in the middle is actually where the testing takes place. And finally, to the right end of the overview that you see is where they receive a report that says, hey, we tested it in all of these mechanisms, all of these contexts, and these are the ones that it's vulnerable to. First, the user provides a client-side call, a JavaScript call for a write method that basically takes in any value and just writes it to the mechanism. The read method would try to extract the same value from the same mechanism, and these will be called separately during these tests. Some of the mechanisms that you'd want to test would vary between needing files. If you're trying to test the image cache, you need to provide an image file and also probably handle a network request path that sends back that image file. So things like that, which tests you want to do, this is where the user comes in. This is the information that the user actually provides. The rest of it, you can use standalone the way it is set up right now. So we have a test suite that that accesses those read and write methods from different contexts. So under first-party embedded frames or top-level frames, third-party contexts, things like that. And it switches between regular and private browsing mode and back, and also tries to clear all browser data and see if you can still access it. To support the existing test suite, you need to create a bunch of contexts. Say we need to create what the domain for the embedded frames will be based on whether it's a first-party or third-party access. If you're testing experimental features that are not out there and enabled by default for existing clients, like say the Privacy Sandbox proposals are hidden behind command line flags. So you'd be able to add that. And also if you're handling course requests, switching on, switching off the cache control headers, things like that. So based on the information that's provided about the tests, the mechanism, the context that need to be used for the particular test suite, we create a configuration that we eventually go on and host in a web server. The server has a bunch of domains that point to it, and it handles all requests that it receives. And if it's a request for a report, it saves that report for access later. Now that we have this ready, we have a bunch of scripts that mimic user interaction. So each time they start with a fresh browser instance and they visit a domain that calls a write method, closes the browser instance, and in a subsequent session goes and accesses the read method, sees if the value stored in the mechanism still persists. At the end of each of these tests, you store all of the results in a database that is then evaluated for tracking vulnerabilities. So based on the outputs of what the read and write method gave, you'd be able to know in what context the current mechanism being tested can be accessed, and as a result, which tracking features they are susceptible to. The way we developed this is we took a modular approach. So if you wanted to add a new mechanism, you'd be able to do it in such a way that you just add a read and write method that interacts with. So we still have, we could test a range of existing mechanisms, and then if a new one gets introduced, you'd be able to add it to the system as well. When we were making the tests, we tried to cover as much of the context that we know of in which mechanisms are misused for tracking. But if there are new contexts within that we have become aware of, it will be easy to add it to the current framework because it's modular as well. We used the framework for evaluating 21 browser mechanisms, and we evaluated 7 popular browsers over 2 years. Of these 21 mechanisms, 4 of them are new and have not been evaluated for tracking capabilities before. The bottom 2, the course pre-flight cache and the client headers, mostly have to deal with the network cache. But the ones on top are 2 of the proposals from Google's Privacy Sandbox. And when we tested them, they were experimental, and one of them is out and can be accessed without a command line flag. This is to give you an overview of the different mechanisms that we tested. They had a varied set of requirements that the current framework can support. So it can go from something as simple as just web API calls for cookies to something as complicated as setting up a parallel HTTP3 server for alt service. This is one of the results that we had when we evaluated all of these browsers. We basically found that in third-party contexts, the number of mechanisms that can be accessed across browsers varies, and even within browsers. And these variations result from adding new mechanisms or introducing new restrictions like origin partitioning, which helps, but it's never stable and highlights the need for these to be tested. Let me give you an example of one of the new vectors that we evaluated within our framework. So Google's Privacy Sandbox proposals comes from this idea that third-party cookies should eventually be phased out. One of the replacements that they have is trust tokens, where the idea is whether or not, determining whether or not you can be trusted to be a human. So say website 1 evaluates you, thinks you're trustworthy, stores some value in the browser. When you, in the future, visit a different website, it can basically learn that website 1 has already evaluated you and thinks of you as trustworthy. Let me give you an example for this. Say you visit Google and Google wants to show you ads. Before they show you ads, they want to make sure they're only delivering ads to not robots, but humans. So they give you a CAPTCHA to solve. Which if you successfully do, they send a web request to their server and ask to issue a bunch of tokens. These tokens are eventually stored in your browser and persist across sessions. So if you close the browser, come back, those tokens would still exist. Now, say in the future, I go to New York Times, and New York Times wants to show me some ads. They also want to make sure that these ads are sent only to humans, but if they show me the CAPTCHA again, I'd be annoyed because I get the same thing every time I visit a new website. Now they can just ask the browser if Google's already verified me, and basically if I have tokens. If I do, they take one and send it across to Google's web server, which basically verifies that this token is legitimate. It belongs to one of those that they had sent out earlier, and gives back New York Times what's called a redemption certificate. The way this protocol is designed, it's based on a 2018 PETS paper. It's called the Privacy Pass Protocol. It's got a bunch of checks. So Google eventually cannot use individual tokens to identify users again. But at the same time, New York Times would not be able to redeem it without sending a web request and making sure that's legitimate. But if you go a few steps back, this is Chrome's specific implementation. There was a point when New York Times asked whether or not I already had a token from Google. This is not part or standard within the protocol. If you notice in this stage, Google did not receive a request, so it never learned anything. But New York Times learned one bit of information, that I have tokens from Google, that I've visited Google before. Now, say if I replace Google with tracker.com. Tracker.com had sent or set some tokens in the past, still there. New York Times can still learn that one bit of information. So the answer for this, whether or not I have tokens, in this case I do, would map to 1. And if I did not, it would map to 0. Think of it as expanding it out from a single domain to 32 different domains. So if I have a token from Tracker 1, I have the response can be mapped out to 1. And if I don't have a token from Tracker 2, that response can then be mapped on to a 0. You build out bits from here and you get like a string of 32 different values, 1s and 0s, that can uniquely be reproduced every time you visit a new arbitrary website, new third-party website, and they persist across they persist between and across sessions. So you essentially have a new unique identifier with which you can map that this particular browser is me for a while. The way you fed it into our system for evaluation, first, the right method is basically if the corresponding bit or the tracker domain needs to be set to 1, you show a fetch request for a trust token, the trust tokens are issued. The way you'd read it is the non-standard part, which is just ask the browser whether or not for that particular domain I have a token or not. We fell into CanITrack, and a rough report that it returned to us is that it doesn't persist between regular and private browsing mode, but it's still essentially a third-party context access. So it's a cross-origin communication mechanism that persists between sessions, can be used for third-party tracking. Now, can you expand it with redirection chains to create a 32-bit identifier? Yes. We eventually used our framework, not just to evaluate this, but a bunch of other mechanisms. And we found a number of vulnerabilities, not just in the new vectors that we presented here, but also in previously reported bugs and vulnerabilities that were not completely fixed. We are open sourcing our tool with all of the existing implementations. With our estimation, it should take an average of, can be as little as around 30 minutes, a new mechanism can be added and evaluated using our framework. But that would depend on the complexity of which mechanism you're trying to test and who the user is. We hope the current framework is used by browser vendors and researchers and integrated into their testing pipeline, and that will provide them a systematic and comprehensive approach to test any new mechanism for privacy invasive tracking vulnerabilities. Please feel free to ask any questions and reach out to me. Thank you so much.
So I feel like your approach is kind of like identify the vulnerabilities in browsers regarding the tracking. So I wonder if the attackers actively exploit the new bugs identified by your approaches. Have you thought about detecting such kind of the attackers, like exploiting those tracking vectors, just about detection, attack detection?
We didn't go and evaluate the top and see whichever second would reach today. The vulnerabilities we found as far as we know are wasn't live reported this, but we don't have evidence of that actively being used in the wild, which is a good thing. I guess because it's aren't already, but it's exploited and it's beneficial for us.